So for the given, the only thing that really matters here is the diagram. This will eventually be included in the free body diagram. So for this one, diagram is enough for what's given. For the find step, this could not really be more clear what we want to find, as it explicitly says what to find, but I will write it down here. We want the tension in that rope that goes from A to B, which I'm going to call TAB. And we want the force in that, I'll assume it's metal, that goes from C to B. And I'm going to call that FBC. Whatever name convention we have here, we need to be consistent in our diagram, in our equation, so that every time I'm talking about TAB, it's talking about the same thing. I don't want to call it TAB here and then Q down here. I also don't want to call it TAB here and TBA down here, because those are different variable names. So I've now set what these are going to be called. Now, the free body diagram, we want to take this situation and I want to make a free body diagram out of it. This is particle equilibrium, so I want to choose the object, or really the point of interest. So what point am I representing with what forces are acting on that point? So looking at this picture, and we also want to keep in mind, what are we asked to find? The tension in AB and the force in BC. So looking at the picture, this one's fairly obvious which point we want, but which point would we want as our object of interest? What are we isolating and drawing the forces that act upon it? Right. Point B is going to be what we want, because point B is touching rope AB, so the force in rope AB will act on B. It's also touching that bar BC, so the force in that bar is going to affect it as well. And it's also holding that flower pot up, so there'll be the weight force of the flower. So by choosing point B, I could choose point C, I could choose point A, but those, I'm not going to get all the information I need from those points. Or point D, I won't get all the information I need. So point B is going to be my object or my point of interest. That's step one. We've decided on it, and I've drawn it. I now need to establish a coordinate system. I'm going to use that X is positive right and Y is positive up. Right? The third thing I need, and really the third and fourth steps I usually combine, I need to put all of the forces that act on point B. So what forces act on point B that I need to represent? What are those forces doing, or what are those things doing to that point at B? Right, so what's one force that's going to act on point B? Yeah. Of what? Right, so there's the flower pot it's holding up that's going to want to take point B and drag it down. So the gravity of the flower pot, I don't need to include the gravity of B itself. We don't know how much that bar weighs. We're going to ignore that. But we do know how much that flower pot mass is. So we're going to have a force from the flower pot that's acting on that point B. And we know we're going to assume that gravity is acting downward. So it's going to be trying to pull B down in the negative Y direction. So what is the force that the flower pot is exerting on point B? So I don't want to say it's 5. It's going to be 5 times 9.8, about 49. And again, this is in newtons. Newtons are a force. This can only handle forces. Right, so the flower pot is pulling down on B with a force of 49 newtons. Right, what is preventing B from being dragged down? Because we know B is stationary, so its acceleration is 0. So what's counteracting that? What other forces act on B? So the rope, we know that for a rope or for a bar, that a force can only act, the force in it acts along its length. So we know there's a force that we already named TAB that acts along the direction of TAB. So TAB, how can we find at what angle that force acts? Yeah. Right, so one way we can do it is it's going to be the arctan of 150 over 80. And in that case, that's probably the best way to find that angle there, is going to be a 62-degree angle. Right, so we can use that geometric information. This is the dimension step. I'm putting in that this is acting at 62 degrees from the negative x-axis. And then we also have a force from the bar from B to C. Now a bar can be in tension or compression. And one thing I want to note here, an arrow coming away means it's pulling on the object, meaning that that thing has to be in tension, or we're assuming it's in tension. The rope must be in tension. This bar, I'm going to assume it's in tension. I'm assuming it's pulling on the object, but a bar could be pushing on the object, meaning that it would be in compression. I always make the assumption of tension and let the math tell me which it is. All right, so this bar, this force in the bar acts along the length of the bar. So what is the dimension I can associate with the bar, the ratio triangle instead? So the ratio triangle, it's a 6, 8. This is the same as a 3, 4, 5 triangle. This would be a 60, 80, 100. So I can just put that this is a 3, 4, 5 to indicate the direction of BC. Either one is perfectly acceptable and perfectly useful for the equation step. So I have the dimensions or the direction of BC. I have the dimensions associated with AB. This 49 is only along the y-axis, so this would be my complete free body diagram for this problem. Again, it has all 4 components I need, and I'm going to be able to use this to write my equilibrium equations in the next step. All right, so I start by getting my equilibrium equations. I will begin by summing all the forces in the x direction. I know, since it's in static equilibrium, I know that the resultant or that sum is going to be 0. So the rest of this, I can refer back to my free body diagram to write the right-hand side here. So what forces, what do I put for my right-hand side, again, based on my free body diagram? Because I only look at forces acting along the x direction, this is where I break it down into components. So TAB is going to have a horizontal component to the left and a vertical component up. So it's negative TAB times cosine 62. That's the horizontal leg of TAB, and it points in the negative x direction. So that's why it's negative up here. FBC is, some of it's in the x, some of it's in the y. So we want, again, how much of it is in the x. We can break it down into that horizontal and vertical component. In this case, the horizontal component points to the left, so we know it's going to be negative. Because I represented this as a ratio triangle, I'm just going to use that to get my information. I know that 4/5 of its magnitude is going to be in the horizontal direction. Alternatively, it would have been fine to find this angle. I forget off the top of my head, I think it's like a 37-degree angle. You're going to get, if you take cosine of 37 degrees or whatever it is, that is just 4/5. So this is equivalent to cosine of this angle, I'll just call it theta for now. That'll give us the same answer. Looking at equation 1, oh, and then I have another force, the 49. How much of the 49 newtons acts in the x direction? Right, it's completely vertical, it's parallel to the y-axis. Looking at equation 1, I have 2 unknowns. I only have 1 equation. So I'm going to just put it aside for right now because it's not yet a solvable system. However, I have another equation when I sum forces in the y direction. Another unique equation. So this is equation number 2. Again, referring back to my free body diagram, I want to include all of the vertical, or the y components specifically, of my forces for my right-hand side here. So for example, I already kind of drew the pictures here. TAB is positive in the y direction. So I will have a TAB times the sine of 62 degrees. That's how much of TAB is only along y. And for FBC, that's also pointing in the positive y direction. It'll be 3/5 FBC. And then what else do I need in equation number 2?
Negative 49.
Right, all of 49 is in the y direction, and it's pointing in the negative y direction specifically. So minus 49. I have 2 equations here, but if I look at my system, I have a total of 2 equations, 2 unique equations, a total of 2 unknowns. So I do know after this step, it is a solvable system. So I can go to the solve step. Now, in more complicated problems, you might write a couple equations, then solve, then go back, write a couple more, and solve. So going between these steps is okay. So I usually try to solve as soon as I can. So if I had only one unknown in equation number 1, I probably would solve numerically right away. It makes it by hand a lot easier to do. All right, so in the solve step, I want to use whatever strategies I can to solve my problem here. Usually I'll skip over a lot of the algebra details. I'll put a little bit in just for the purposes of this problem. I can start with equation number 1 and make a substitution here. I can put TAB cosine 62 on my left-hand side. And I can isolate TAB. I would probably put this as a decimal. I didn't do that in my notes though. But I can isolate TAB and say it's negative 4 over 5 cosine 62. Whatever that would be as a decimal would be okay. I can take that, again using substitution, and put that into my equation 2. So everywhere I see a TAB in equation number 2, I replace it with this stuff. It's just some number times FBC. By putting that into equation 2, I now have an FBC here. This is replaced by something times FBC. So the only variable in equation 2 will be FBC. So from that new equation 2 with the substitution, I can find FBC. And if I do that, I find that FBC is a negative 54 newtons. I can take that result and go back down here to the substitution. Now that I know this as a number, I can multiply it by negative 4/5 over cosine 62, and I get that the tension in rope AB is going to be positive 92 newtons.